one particle to two particles. Okay, so now we have two electrons with two spins, right? So just one more thing about the single, because I'll need it later. From now on, as you know, in quantum computing, we prepare usually the qubits in 0 or 1. So up or down. That's usually what goes into the gate. So we want to know what happens to up and down, where you go through all the different Pauli matrices. So what does sigma z do to up? Sigma z to up? What?
Nothing.
Because it's the eigenvector with the eigenvalue 1. What does it do to down? You can either do this, just multiply this, or you can remember that down is the eigenvalue of sigma z with an eigen
Minus.
So that's minus d. You don't see it, just do this times this, you have minus 1 times minus 1, you will get the minus of this vector. Now remember what this do to any vector? We've done it once.
Rotation around the axis.
So what does it do to up?
Down.
And what does it do to down? And then this is kind of similar, but what will it do to up?
Half of it down.
What will it do to up? Just put 1 0 here and tell me what it does.
Minus I did down.
Give you 30 seconds to check it and see if I made a mistake. And this we will use now a lot. And sometime I will just delete all of this. And remember these two will be used, okay? See the average. Okay, now we go to two particles. We need to set the rules of how do we deal with a system of two particles. And of course, if for each particle we have two possible results, then when we have two particles, we have four possible results, right? That's understood. You can either get on particle 1 up, particle 2 down, or up, or down, or down. We have all four possibilities, and since we have four possibilities for our measurement of the whole system, we need four-dimensional complex Hilbert space, right? Like we did here with two-dimensional complex. The I is here. So now we will have a four-dimensional.
Just say it's sigma z, right? Because you wrote with
It doesn't
sigma
matter.
z.
It's true for any sigma n. That would be, here I wrote z, no, right, n. Okay, so the system you would want to present by the four different options. This always will say particle number 1, and this will say the state of particle 2. Could write U1 and U2, but given the order that I will keep, I can get rid of one index. There will be a lot of indexes, so it's better to not do it. Okay. But unlike that, when I do the matrices, so I say which magnet I put on each electron, for some reason it makes it easier to say that sigma matrices are on particle 1, and we will do the same just with a different letter called tau z on particle 2. So anytime I want to say I'm doing something to particle number 2, I will use tau, Same matrices, it's exactly the same matrices. Just give them a different name so we know that when I say tau, I mean I'm putting a magnet in direction z on particle 2. If I say sigma, I mean I put a magnet or a magnetic field at the direction of z on particle 1. Okay? So we have 4 different states, UD, EU, and DD. We'll soon show, but logically you already understand they need to be orthogonal to one another because they're different states of the whole system. And they will be a basis of the 4-dimensional complex space. Okay. Now I'll do that just for a second and we'll mostly forget about it. But we said we know to do this, to get from a 2-dimensional to a 4-dimensional state, we do this tensor product. The vector u was 1, 0. Now we want to multiply it and get a 4-dimensional vector. So we do 1 times 1 is 1, 1 times 0 is 0, 0 times 1. Okay. And naturally, what you'll get out here will be the natural basis of a basis of the 4-dimensional space. And of course it's a complex space, even though you don't see it here, but we allow to multiply by I. Right? The vectors and the numbers are all complex. So the fact that you don't see I is 4, like you didn't see I here, but it's still a complex space because we allowed, it's within the rules to multiply this vector by I, or to multiply this by I and get this. So we're in a complex space. If we have 4 complex numbers, how many choices of real numbers we have?
8.
8, right? How many choices did we have here?
4.
4. And then we said we ask only for normal vectors. So we came to 3 choices, right? And then we said we don't care about the phase because to get the expectations of the physical experiment, we do the square of each number. So it doesn't matter if you have a minus, and we get 2. If we do the same here, so we still want normal vectors because remember the normality means that the summary of all the probabilities is 1, which is whenever you take probability. So we use only normal vectors. So we get 7. And then the phase again doesn't change anything in terms of physics. You get 6 dimensions of choice, freedom. This is already strange. Why? Because if here we have 2 choices for 1 particle, you would expect 4 choices for 2 particles. But we have 6 choices, and not 2, and not 4, sorry. Which means this vector space has more freedom than only multiplying vectors from here. And we already showed that because we said this thing, AB, tensor product of CD, the definition is AC, AD, BC, PD. That's the vector that we create from 2 vectors that represent the state of particle 1 separately from particle 2. If they're separate, we can do this, and we get that. And that's a special vector. It's 4-dimensional, but it's special. In what sense? That if we call this V1, V2, V3, V4, we see that we have a ratio that V1 divided by V2 is C divided by D, which is also V3 divided by V4. So the ratios of this vector is special. And these are all the vectors that we get from multiplying a state vector from one particle and a second particle. We will necessarily get this ratio. And as I said, if we do 1, 2, 3, 4, that's a vector in 4 dimensions. So we take V1 divided by V2 is half, and it's not the same as V3 divided by 3, 4. So this is the different perspective to say the same. We have, if we create the vectors out of these state vectors, we will get only a subspace, only a subgroup, subset of the vectors. There will be other vectors that are not possible to break into these two. If, I don't know, like I didn't show that, but if you could do, the question is, can you take this vector and present it as A, B, cross CD, anything, any number? Can we do that? The question is no, because if we could do that, then you would necessarily have this, and you don't have this. So this is inseparable. Okay, you cannot break it into two. It's kind of richer or different from what you get just from the 2 times 2. That gets you 4. This is a subspace of 4 dimensions, and we are playing in a subspace of 6. So there are several vectors. This is not normalized, but you can find normalized vectors, just normalize it, and you get a normal vector that represent the state of these 2 particles that is not breakable into this. Why? These are the entangled states, and they're very special. They cannot be broken into 2 separate states, which means you cannot, entanglement is a phenomenon that you cannot know everything about the state of each of them. They act in some mystical way. They only exist together. So you can never break this into 2. Okay, so remember that, but we will mostly not use it. We will just keep to this thing, and remember that behind it we have all of these strange things. And now, of course, if this is the base, we can do any wave function or state that is any, well, it's the letters thing, right? Let's do alpha UU plus beta UD plus gamma DU plus delta DD. Just numbers, because I don't want to mix the English alphabet with the Greek alphabet. That would be maybe, I don't know, maybe I'll come back to regular numbers. But these are complex numbers, and these are the vectors that are the basis of the space. So each state we can represent as a superposition of these 4. And alpha, beta, gamma, and delta, we can choose whatever we want. As long as alpha square, b square, gamma square, delta square is equal to 1. Now you cannot do the sphere, the Bloch sphere of this anymore. Like, it's 6 dimensions, no way. You can do 2 Bloch spheres and say this is here and this is here. Okay. Now we want to look at one of the special states, the Bell states, which is the entangled state, which is psi equals 1 times square root of 2. Well, it's much harder to say it in English. UU plus DD. What is the significance of this? Immediately as you see it, it means that if we measure the first particle and find it at U, it needs to collapse to the ingredient that says U, because we found the result is up, so this is irrelevant, it collapsed to that. But because they're entangled in this specific way, it means that only also the second one is at up. And if we find D on the first, it means that the other one after the measurement also must be D. It's not true about here, like, right? If you have this state, which is not entangled, and you measure the first particle and you get up on the Z direction, it will collapse to this one, right? Because it's up on the first particle. We didn't measure the second yet. It will not be these, because we know that the first one is not D anymore. So if we had this state, we measured only the first one on the Z direction, this will be the result, okay? But this still allows the second one to be up or down, so they're not correlated. But only this special state and several others like UD plus DU, this will be anti-correlated. Whenever we measure this is up, we know the other is down. These are the entangled states or the Bell states, which are special in the sense that when we measure one, we know the result of the other 100%, which is not true in here, okay? Because here you can measure the first and find out that it's U, but you still have the two options for the second one, okay? And it may be up or it may be down in different probabilities depending on the alpha and beta. Yeah?
Question. Entanglement relates to the
What?
באנגלית או עברית?
English is better.
Okay. The entanglement doesn't relate to the fact that we measure them in the same result, or let's say that we took two entangled particles and then we rotated only one of them to be down, for instance. When I'll measure, it will be up and down or down and down?
Wait, I chose, again, playing in a four-dimensional space, I can choose any linear combination of the four vectors of the basis. There are many choices, like soon we will see if I choose psi to be up. This is also a state, it's an eigenstate.
So it's alpha.
That if I measure U, I know the other one is U. But I don't need to measure because I know both of them are up.
It's alpha.
So there's nothing special about this. This is also not special. Here there's something special. Which is that I don't know the state. I have half chance of measuring up or down. But I do know that if Alice measures on one, she knows the result of two. So we'll see that it's a strange situation in many ways. And it's a very big question, what's strange about it? And we'll speak about it because we do Bell theorem in a moment. Einstein thought the most strange thing about that, because Einstein invented relativity, is that it allows you to do non-local interactions, strange ones, spooky action at a distance. That was the characteristic of what he saw. Schrödinger, who thought about this strange state first, before Einstein and EPR, he thought that the interesting thing about that is that it's inseparable as a vector. We'll show that in a moment. So it's a strange state in the fact that you know exactly, this is a state in 4 dimension, right? It's a 100% superposition state. Okay, it's a kosher state. We know exactly the state of the system of the two particles. But since this is one of these strange vectors, you cannot present it as one vector n and one vector m. You know we have many vectors, right? But you cannot measure, it will never be equal to this. Now we know that on one particle, x is 1 over square root of 2 of up plus down, right? So this is a state and this is a state. Here in the 4-dimensional, this strange entanglement means you cannot, it's not separable, you cannot present it as a multiplication of two vectors from the regular spaces of the separate particles. So Schrödinger, for him, the strange thing about this system is that you know everything about the two particles, and yet you cannot know exactly what the situation of each of them separately. And this is also non-classical, because in a classical state, if I have a billiard pool table, and let's say I come out of the room and say, now I know everything about the whole table and the whole balls. It means immediately that I know everything about ball number 8, and I know everything about ball number 6. So knowing the whole system in classical terms, logic, means I know everything about each of the parts of the system. In quantum mechanics, that's what Schrödinger thought, the strange thing is about our knowledge of the system. We can know everything about two particles, and yet don't know about each of them separately. It's a strange thing, but we'll see many more strange things about it.
So when can we use, or when do we use entangled particles that are not in Bell state, that are not definitely inseparable?
There are many ways to entangle in quantum computing and in physics. We only use the 4 Bell states.
So we don't use the other states?
No, but it's not, you can't achieve much, I think, from them.
Okay.
Because this is also a base. There are 4 of these. And you can show the orthogonal, we'll show that in a moment. So there's UU minus VD, there's UD plus DU, and there's UD minus DU. Now, like X and minus X, both of them give half-half when you measure them on Z, right? So in terms of measurement on Z, they behave the same. That's what I meant when the phase doesn't, then well, it's not really the phase, but they're the same. But these are exactly like you have 4 of them, there are different states. Some of them have the same prediction on certain measurements, but these are the 4 Bell states. People use this one mostly, but the results will be the same. I don't remember what I use there. I'll stick to that one to do the Bell equation. I think I use the singlet. Yeah. Right. UD minus D. So we stick to this one now. Okay. I'll try to remember. Okay. So, despite the fact that we wrote them in the same vector, because it's a 4-dimensional vector, when we do an experiment on one, we don't influence the other, right? They can be like years light apart from one can be here and the other at the end of the galaxy. We describe the system of both of them, but we can have a magnet applied to one, which will not influence the other. So we can measure, we can take them through polarizers, we can take them through magnetic fields separately. So we have to have sigma x and we have to have tau x.
But it will influence the other one.
We influence the joint state, the state of the whole system. Of course, if your interest now is in a system of 2 particles, and one of them is influenced, the whole system is influenced, but the second one is not, at least initially. With your common sense, you think you can walk on one at the end of the galaxy, it will not influence. So I can apply a magnetic field
the
sigma
result
z
showed the
here
other
and
one.
sigma x there.
The result showed the other.
As we remember, we showed the matrices do not multiply symmetrically or when we place the order of them, which means we cannot on one particle, we cannot measure sigma x and immediately also sigma z because it changes because of the collapse. We cannot do. If we do sigma x and then sigma z, or the opposite, we get different results. But that's on one particle with 2 orthogonal bases in K.
May you please repeat why the up, up, down, down states are inseparable?
We'll show that in a moment. But again, up, up is 1, 0. That's what I tried to do and I still owe you, but I'll do that separately. And the combination of the 2 is this. Try to separate them at home.
When you use the
Try to write them as AB times CD. Try to do that. This one.
Because it can't be described as a tensor multiplication?
It's kind of, you don't have the ratio Z because of the 0, but it's I think it's kind of easy to prove like this. If you were able to do it AB, CD, right? If you were able to do that, then here you have AC, AD, BC, and BD, right? Now, if AD is equal to 0, it means that A equal to 0 or D equal to 0, right? There's no other way. Right? If you have 2 numbers that multiply, or both. It means that either A is equal to 0 or D equal to 0. If A equal to 0, this should have been 0. If D is equal to 0, this should have been 0, so you can never separate.
So every
End of story. So it's an inseparable vector.
So every unentangled state is a product of tensor multiplication.
Again?
Any unentangled state
Kind of, yeah.
is
I don't want to say what yeah, okay, for us. Okay, so let's see what else is strange. It all comes from the same strangeness, but you can see it in different ways. So that's what we'll do. let's just understand how we work with this. So, for example, sigma will always operate on the first parameter, because sigma is on the first particle and not on the second. Okay, so if I have sigma x of uu, it will be what? Hmm? So it shifted u into d, like we've seen here, and it gives this. And if I ask tau x on uu, yeah, this one works on the second element, and like sigma x, tau x is taking u and making it into d, so it will be ud. I didn't tell you how it looks as matrices, like both of them, like when we do sigma x, tau x on uu, what will it be? They don't interfere with one another, each of them. Yeah. And if we do tau x, sigma x uu, it also gives it. So the matrices of tau and sigma can be replaced because each of them works on a different system, so it doesn't matter. Unlike sigma x and sigma y, which you cannot replace.
How do you represent the
In four
separate?
dimension.
I mean, no, the separate in reality. How do you create two separate systems?
Like one to the end of the galaxy and the other here.
As long as they're not
Theoretical,
entangled, they're separate actually.
So kilometer away, usually if you have a small magnetic field here, a kilometer
Ah.
away you would not feel.
Okay.
Separate system is pretty much the opposite of entangled. So any system that is not entangled is pretty
That's
much
what he
separate.
asked, yes, for us, yes. Okay. Now let's see what happens to our entangled state, which we said will be from now on this one, ud minus du. Let's see what happens to it when we do sigma x. Of course, we can represent these as four-dimensional vectors, and this is a four-dimensional matrix. I just will show you how you do that, and now you'll never see. So you have 4 and 4, right? So this is 0, 0, 0, 0, 0, 0, 0, 0. And if you want sigma x as a four-dimensional matrix, which means this times the matrix I, the identity of the second, like you do nothing on the second one, but you do something on the first one. So here you will have sigma x, and here you will have the identity. That's the matrix. And if you want to see the matrix of tau x, it will be the same, but the tau will be down here. So this will be 0. Here you will have zeros. Here you will have zeros. And here you will have the identity matrix. So this will work on four-dimensional vectors and get you the results that you want. But this is too complex. We don't want that. We just keep using this dictionary here. Then you'll see it works very well. If someone don't see why it works, go back and do the multiplication and you'll see. Okay,
Can I
so
see
now,
this?
just a second, we now want to do this one. So any matrix on a number doesn't matter, we can take the number out. So we have 1 over square root of 2. What does sigma x do to ud?
DD.
Yeah, so it's dd. What sigma x do to this? Okay. Now I want to take this, the result, and multiply it. Let's call this psi. Okay. Now I want to take the results. I've done sigma x psi. I got a vector, a different vector. And now I want to do psi, sigma x, psi, okay? So this I've already calculated, this one. And now I want to multiply it with the bra of the original one, okay? Keep your head straight. I do 1 over square root of 2. Now I have the bra.
supposed
So
to be
the
zero, no?
the bra is UD minus DU. I just changed the direction of this little arrow. And this will now multiply not this, but the result of sigma x psi, which is this. It's again square root of 2, so I have twice square root of 2, it's 2. And now I have DD minus UU. Okay. So now we know this is a basis, right, of the 4-dimensional, and we've seen it's 1, 0, 0, 0. So UD times DD needs to be 0. We don't have anything identical here, so this times this is 0, this times this is 0, this time this is 0, and this time this is 0, so we get 0.
And you could say because this is the average of the
Now
result.
someone needs to remember it because I don't think I wrote it in the homework. Now you can do the same for sigma y, and you can do the same for sigma z, and you will get 0. Which means, remember, sigma n was n1 sigma x or plus n2 sigma y plus n3 sigma z. And now you can see easily, or check it at home, it's more complex homework, that if sigma x psi psi is 0, psi sigma y psi is 0, and psi sigma z is 0, then also psi sigma n for any n will be 0. Because it's just a combination of n1 times 0 plus n2 times 0 plus n3 times 0. So this will also be 0. Which means, believe me about the algebra, or do it yourself. We've done one. Which means, this Bell state, okay, I have now 2 entangled particles, and now I'm trying to work only on one particle with a magnetic field in any different direction, and I get the average, this is the average, remember? The average of my measurements on any direction is 0. I do the average on measurement on one of the particles only, is entangled to another one, but on this specific one, any direction that I put, I get 0, 0. That I get half chance of getting radiation or no radiation. That's the meaning of an average of 0, right? It means the exact number of plus ones and minus ones when I do the measurement. Which means, in the entangled state, we don't have any direction on the sphere in which this will surely go through. So if we thought that we saved ourselves on one particle and said, okay, it doesn't have a real spin like a ball with a spin, a macroscopic ball with a spin because it behaves this strange Stern-Gerlach. But still, on one particle in 2 dimensions, I have always an angle where it will always go through. So maybe that's the real spin. When you get to 2 particles and you entangle them, then the single particle don't have any direction. In all directions, it will give you half-half, which means there's no certainty about any direction. It's always half-half. That's, again, something special about the entangled state. That's why you probably didn't notice it, but when you do this game of Ofer with an entangled state on a Bloch sphere, if you remember, it showed it as a point here, because it doesn't have any direction that you can assign to it. So
Showed
the
what?
entangled state,
Showed what then?
what?
What did you show there?
You have, for these states, you always have a direction, a vector, like this is up. This is
I just didn't
X.
hear what you said.
I said, when Ofer showed on this game on the
Mhm.
computer an entangled state, a
And
Bell
then
state,
it's okay.
then the computer drew it as a point at the middle of the square because it doesn't have any direction.
But there was a line there or something.
No, the line was only when we worked on single states or non-entangled states. Okay?
It was in the game or in the simulator?
In any simulator, any software of quantum computing, when you have a Bell state and you try to put it on the Bloch sphere, you will have a point in the middle. Which I think in regular optics, when you do Poincaré sphere, which is the same, you don't get entanglement because you work with classical optics. You have polarizers. In regular optics, you never get entangled state. For an entangled state, you need to really take the light to the quanta of light, which is very, 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 very small. Therefore, in the 1980s, only ASPE was able to control single photons. It's not trivial at all. But nowadays, you'll be in Weizmann and show you. We hear clicks of single photons.
I didn't get you. What is it? What isn't possible with light?
You did use Bloch sphere, right? You called it Poincaré sphere.
Yeah, it's the same mathematics.
But you never had, if you did classical optics, like ELOPS or fiber optics communication, you never had a point in the middle, which means there's no polarization to the photon. Each photon had polarization. It could be circular polarization, anti-circular polarization, this polarization, that polarization. You always thought you have polarization. You never played with entangled pairs of photons, and therefore you never had this situation when the photon don't have direction.
It's true, but all it means that entangled state is something you need to prepare.
It's something quantum, and you didn't play with it if you're playing with regular optics.
True, you need to prepare it.
Yeah, but in fiber optics, when you do communication with photons, you don't care about the quantum state. You just use photons 0 and 1. I have a photon in 0, I is 1, I don't have a photon in 0. So you don't care about the polarization, and it's usually also not kept along the fiber optics. That's why communication with quantum states is more difficult.
So the average is not doesn't have direction, or the
What?
particle doesn't.
The average of any measurement, thousands of measurements in any direction would be, the average would be 0, which means any direction, the first photon, as long as it's entangled to another one, which is way apart, still don't show any special direction. It doesn't have any special direction. In all directions, it will show 0, which means half chance to get up and half chance to get down in the direction that you choose.
Is it a phenomena of the system of 2 photons?
Yes.
Or, and if you go to 3 photons, you
Yeah,
get.
you can entangle 3 photons. That's what they offer yesterday called GHC, like up, plus down, down.
But they
You
show the
can.
same
Yeah, you
property?
can.
And then
Same.
if you measure a polarization or a spin of one of the 3,
Same. You will not see any direction.
okay.
So basically, the actual entanglement loses one of its properties in a way. Just loses information.
Okay, that's a good question that holds only for the next 10 minutes, because you assume there is a characteristic or property called spin. As I said, you stick to the poor people solution and you say, okay, here there's strange behavior in the Stern-Gerlach, but still there is a direction, because I can always find for each vector, each state of the system, I can find the direction in which I get 100%, and I want to ascribe the property of spin to this one. But as I take you to 2 photons, you lost this. You don't have any direction to the first particle. You cannot ascribe any direction to the first particle, because on each direction you get an average of 0.
So in a way, let's say that I take 2 photons that I continuously emit them and entangle them.
Mm-hmm.
So, and then I'm going to measure with the diode the power of that. The first beam, I'll see 0. Because they're always being entangled, and on average, I wouldn't see any.
Yeah. I think that's it. That's the strange thing, and you can say it's strange because it doesn't have a spin. You can say it's strange because it's inseparable, the vector of these 2, and you can say it's strange because you can create spooky action at a distance. You can say, I know everything about the situation. This is a vector in 4 space. I know it. This is the vector. This is the state of the system. But this specific state of the system, you can never present it as a multiplication of 2 states of the single photons. If you could, you would know that this is n and this is n2, and you had directions, but you cannot, therefore they don't have directions. But you can still say, okay, there's some kind of a hidden variable which at one point we will know, and then we will ascribe this property. That's what Einstein said. And now we will show the Bell.
I have another
Inequality.
question. The probability is always 50%, or it might be,
In this situation, yeah,
so it's always for any,
since the results are always +1 or -1, if you get an average, it means half-half.
so you cannot actually be in a superposition where it's not 50%.
No, you can, but not in this specific state. Like if you take third DD plus 4/3,
Mm.
it will still be entangled here, with different probabilities. But here in this state, because I have 1/2, it means that it's half-half, and therefore the average will be 0. Okay, strange. Now it's becoming more strange. Okay. So now let's go back to Einstein's Podolsky and Rosen argument and understand it, because it's a deep philosophical argument, and most physicists don't like or don't know philosophy, so they really, many of them don't understand what Einstein wanted to say. And therefore, it's difficult to understand what Bell said, and therefore it's difficult to understand what the inequality says. Okay. So Einstein finds out about this state, not exactly it's entanglement, not in spin, but in position and velocity. The mathematics of which is more difficult, so it's difficult to read the paper. And also the paper opens up with a statement of philosophy, coming, I think, from Podolsky, which says, here's a criterion of reality. Okay? Like, we want to speak about what happens to the photon or the electron when we don't watch it. Okay? Which seems to be non-physical, right? If you're what the philosophers call positivist, you say, I see only what I see when I measure. Measurement is when I look at it. What happens when I don't watch something, like this tree in the forest that no one watches, it's nonsense to speak about it. It's like, you don't need to speak about it. You speak only about things you see. When I don't see them, they can be ghosts, they can be whatever. I'll never know, because if I want to see if they're ghosts, I look at them, but when I look at them, I'm also already measuring them. So some of the physicists are saying, no, quantum mechanics give us the predictions of any experiment, gives it in a perfect way. We've never seen an experiment that doesn't work like quantum mechanics, therefore, excellent theory. It says strange things about being in superposition before you measure it, and depending on where you put the measurement system, you get different results, but it doesn't matter. When you do put the measurement, you get the results exactly as quantum mechanics says. Half-half, 0-1, third, fourth, anything, it goes perfectly. Einstein does not think that's physics. Einstein thinks physics is about God, which means about nature. Because Einstein read Spinoza, and Spinoza says God is nature. So when Einstein says God, it means nature. He says, I want to know about nature, not about what happens when I measure nature. My theories are about nature in itself. Sometimes I measure nature, sometimes I watch it, but I want to have theories about what really happens to particles, and that's realism. I think there are particles not only when we watch them. Unlike the movie Matrix, there's no world, there's only pictures that some... Einstein don't believe that because he read Immanuel Kant, and if you read Kant, you cannot believe the Matrix. And the fact that I see a bag and I tell you go and pick the bag and you go and pick it from the same place, it makes the probability that someone is playing with our minds far less possible. Immanuel Kant, different story and a different bootcamp. But Einstein believes there's a world. Without watching him, what philosophers call ontology, what there is, and epistemology is what we know about the world. So Einstein is interested in the ontology. And he says, in quantum mechanics, you allow these strange things called superposition, which means the particles don't know what is spin. And that's impossible. If there's probabilities, it's only because we don't know enough about the particles. The particles will always have the property either spin up or spin down. If we say it's half-half, it's like when we have coins in our hand, and we mix them and say, what's the possibility of having the 5 shekels here? And you say half, which means I don't know. But we both know that certainly there's either 5 here or 1 shekel, but not both of them together in superposition. That's realism. And Einstein wants to have realism also in the microscopic world. So that annoys him. And he wants to say something about the spin of the electron, not when we measure it, but also when we don't measure it. And because quantum mechanics says that it's superposition when we don't measure it, and Einstein don't like it, says surely quantum mechanics is not wrong, but it's incomplete. Why incomplete? We need another property that will allow us to say this 1,000 electrons, that one came up, one came down, and they seem to be exactly the same. There must be something not the same about them. Half of them came with the property, the hidden variable G, and the other one came with the hidden property P. And we will find the law of nature that says that if you come with G, you go up, and if you come with P, you go down, and therefore it's deterministic. Bohr, of course, does not agree. He has all these tendencies of Buddhism, yin and yang, and he says, we found out that there is superposition. The theory says there is superposition. Therefore, there is superposition. There is no reality like we know in the macroscopic world. There's only superposition, which is a strange reality, but that's the reality. Get used to it. And not only that, if you add to it the Schrödinger cat, and you say, okay, we are made of atoms, the atoms can be in superposition, so we can be in superposition. Why we do not see it? Maybe because of the measurement, maybe because of other things. But in principle, also the macroscopic world allows us to be in superposition. That's what we learn from quantum mechanics. Einstein said it cannot be like that. Bohr says it can be like that. Each of them is trying to convince the others to be on his camp and on the other. Bohr has more money. They say here, why Bohr had a lot of money? Because of the Carlsberg beer. They're Danish, very, very rich, and they support Bohr. They build this institute, they give him a lot of grants, and therefore Bohr lives in the palace of the Carlsberg family. You can go to Copenhagen and see that. And they have a huge villa for him, and he has another building, and that's Bohr Institute. He has a lot of money. He can send money to Heisenberg, to Schrödinger, to bring them to stay with him. And when they stay with him, he takes them over. Heisenberg, he took 260 miles walk outside of Copenhagen, and that's enough time to convince him about the complementarity, and that's how Bohr functions. Up until today, this villa is the home of the best scientist in Denmark for his whole life. It started with Bohr, and from then on, if you go to that place, you see the best scientist of Denmark.
This is why Microsoft established their quantum center.
Yeah? Okay. So this goes on and goes on, and since they do like philosophy, although they're not professional philosophers, they keep that. And in 1935, Einstein comes up with the entangled state. And then he says, look, we have these two particles, now not at the end of the galaxy, they're both produced at the same place. One, two. Later on we call this Alice, and this is Bob. And they're entangled. The state is the one that we wrote. Psi of these two particles, I don't tell you how we do that, but we do that, is 1 over square root of 2, up, down, minus, down. Okay, so now it's not about a single particle, the superposition, and can it be reality that we have superposition, it's about two states. And to really prove that he is right, so it's not now a matter of do you like reality, realism or not, we all believe in relativity. And relativity says, without us studying relativity, that you cannot influence things quicker than the speed of light. So if you put two things far enough, and you do an experiment at a time where no photon can move between the two, like you have 10 seconds of an experiment, you need to put them apart 10 seconds times the speed of light, and if it's more than that, there's no influence possible between the two. That's what we call locality. And why is that so strong? Because in relativity, if you manage to do that, you can do all kind of crazy things, like kill your grandfather, go back in time, and do all kind of crazy things that we really don't want to have in physics. So now Einstein said, what?
You still have to
Yeah,
Not before you were born.
before you were born. Okay. Now Einstein said, look, this is a superposition of the two particles system, right? And Einstein, I don't believe this is possible. This is only us not knowing enough about the hidden variables. At one point in the future, I will find the theory, or someone else will find, or we add another something to the system, and then we will know this is the spin or this is the spin. Cannot be both. Okay. So now let's do what you both think. So you think that this is really the situation of the particles. This is the real situation. And now the two particles are progressing with this state. Whether this state changes according to you or in the axioms of quantum mechanics, only when Alice decides to measure the direction z. She puts a magnet and a measuring system and she measures particle 1 on z-axis. And she will get what? Either +1 or -1. Let's say she gets +1. Then we know from axiom number 7 that it's up. And after the measurement, particle number 1 is up. But he had only two options, this and this. This is not up. So we know for sure that the whole system is in this situation up-down. Which means that the whole system is up-down. So this is also an up-down. Which means that after the measure, this is like 10 a.m. Before 10 a.m., both particle was part of an entangled particle, so it was in superposition of up and down. After the measurement is in up-down, therefore 100%. If he measures now z, he will get down. Okay. So now the argument works like that, as it is in the EPR. We said the reality criterion is if, that's what Podolsky said. If you can measure a property of a particle without disturbing it, and you have certainty, 100% certainty, that you know the property, so you measure a ball for its color without disturbing it, and you know it's yellow, because you didn't disturb it, it's certainly yellow. So there's a real property in the world if you're able to measure something without disturbing it and get 100% certainty about the result. That's the reality criterion of Podolsky. And it's completely philosophical. You can argue about that. But the common sense says it's right. Right? You measure something, you know that you didn't disturb it, because if you disturb it, then it's not true. But you know you didn't disturb it, and you know the result is 100%, not 90, then you know the property belongs to the particle. So what happens here? Alice can know for 100% before he measures, without disturbing this, because this is far away and relativity does not allow any disturbance to go faster than the speed of light. So surely she did not disturb it. And she knows for 100% before he measures that the result will be D. And if he measures, he confirms that. Therefore, we must say that D is the property of particle number 2, even before Bob measured it. So even here, before 10 a.m., we must say that it was D. But this is not what quantum mechanics says, because it says that before she measured, it was a superposition of D and up. So, because we have this criterion of reality that says that if she can know something 100% about something she didn't disturb, therefore this is a real property of the real electron, and therefore it was its property even before she measured, and therefore quantum mechanics is not complete. Okay? It's not wrong because you'll still get the same results as quantum mechanics says with the axioms, but we found something about this, the reality of the particle before we measured it, and in reality without any connection to what we do. The possibility of her to know something for 100% without disturbing it means that you must say that this specific electron had the spin down even before she measured. And if she got down, you know that for electron number 123 in your experiment, surely with the hidden variables theory of the future, it will have up. Because she measured down, this will certainly have up. And since quantum mechanics describe the state of the system as this before she measures, and it's not this because they surely had something before, it means that quantum mechanics is incomplete. That's EPR. Bohr writes a response, Schrödinger writes a response. Bohr actually writes a response with the exact same title of the article as Einstein-Podolsky-Rosen. As always with Bohr, you can read it. It's something about complementarity and the world is strange and so on. So it's not conclusive anything. And really, it drops, if you watch this Klauser video, it really shows a graph of the citations of EPR. Like how many citations they got in the scientific literature along the years, starting from 1935. And that's the number of citations. This is the way people measure the, and it goes like this. It's like until the 1980s or something. So here you have one of Bohr, one of Einstein, and almost nothing. And today you have about 2 per day. Articles that quote, and Lauser says in the video, he says it doesn't mean that anyone quote really read the paper, it just means that they quote the paper, because this is the basis for Bell and then for any quantum qubit in entangled state. So no one was interested in that because again, for the physicists, of course, as 1939 came, there was a war, and then there was a Cold War, and the physicists were busy building radars, atomic bombs, transistors, computers, and they lost all appetite to philosophy. Seems inconclusive. Okay, you say something about what happens to the electron when we don't measure it. Bohr says something different. We can argue between Buddhism and the Western culture as much as we want. Not interesting. Let's build something. And that goes on for 30 years, 1931 to 1964. Then John Bell, an Irish physicist working in CERN, like all the others that I mentioned, he was told, like you will be told today, don't do this, you will lose your future in science, you will never be able to get a position as a physicist, do something else. So Bell went to CERN and did particle physics, the mainstream physics, but in the evenings he was still interested in this puzzle. And it really seems impossible to do something to prove who's right, Einstein or Bohr. Because how do you say something in an experiment about what happens when you're not measuring something? Like, it seems logically impossible. Like, if you want to know something about it, you need to measure it. But if you measure it, both Bohr and Einstein will agree what the results will be. It will be half-half. So the whole argument seems out of questions for physicists. And Bell wants to do what Einstein wanted to do. He wants to find a hidden variable theory that will make this deterministic and therefore settle the... By the way, the opposite, what you don't see in EPR, but soon it will become very important, it's a different way to look at it. So Einstein said something in EPR about the reality, and since he has a criterion of reality and he fulfills the criterion of reality, says this is not the true situation, this is the true situation. But the same goes for relativity. Like now, if you say, let's say Bohr is right, and this is really the situation in the reality itself, not this. There's no hidden variables. Quantum mechanics is complete in describing the world right. So the two particles really, not because we don't know something, really they're outside in the world, they're really in this situation. There's possibility of a Schrödinger cat. You can have two particles in superposition. And only, like the axiom says, only when you measure you get to this one. So when she measures, something happens to the whole system, really happens, not we gain knowledge. And the system was there already. Like the system really is in superposition. We measure, we collapse the wave function here, and therefore we collapse the wave function there. So the state of the system really changed faster than the speed of light. Okay? So there's a real change faster than the speed of light when she measures if Bohr is right. And that's the spooky action at a distance. Okay? Because something happens. The wave function of this particle is collapsing from a superposition to a vector that is not superposition in 0 time and faster than the speed of light. So this contradicts relativity. Lichora. How do you say lichora in English? Prima facie. Okay. So 30 years and nothing. And now comes Bell. And again, Bell's original article is more complex than that, but this is the rendering of Zuskin. It's much simpler. So Bell is saying, let's say that Einstein is right. And let's say there is a real property of spin. It was all along down, but there's an hidden variable we don't know. And with this hidden variable, the whole strangeness of this business will change, and we will know exactly what the spin is. And if we know exactly the spin of the particle, we also know the projection of the spin on x, y, and z, right? If there's a real direction, we also know what sigma x is, sigma y, and sigma z, perfectly, like without any probabilities. So we'll have 3 different properties of the real electron in the real world after we finish finding the theory that completes quantum mechanics. And therefore we'll have 3 properties, sigma x, sigma y, sigma z, of each electron. And we deterministically know them. And now it says, Bell, any 3 properties, A, B, and C. 1, 2, 3. How did we do? 4. No, 1. I think 1, 2, 3, 4, 5, 6, 7. I think. Anyway, just to be consistent with my note. Any 3 properties, like as I said, like tables, color, red. Tables that are square, and tables with 3 legs. 3 properties of tables, real properties. Some tables are both red and square, but have 4 legs, so they're not with 3 legs. Some tables are red, square, and have 3 legs. Some tables are with 3 legs, but they're green, and they're not square, and so on. Okay? So this represents the logic of properties, the very, very basic, simplest notion of what a property in reality can be. And there is an inequality that describes this. For any property that is a real property of a real object, then we have that A and not B plus B and not C is bigger or equal to A and not C. Let's see that this property of A, B, and C is true. What is A and not B? That's A, not B, will be this one. Right?
The first
1
order.
plus 4. What?
The
Oh. This is how we write A and not B. Someone didn't see. If you want, you can write it A and not B. Doesn't matter anymore. This is 1 plus 4. What is B and not C? This. 2 plus 5, right? And then we want to see whether it's true that this is bigger or equal to A and not C, which is 1 plus 5, right? Everybody see? Yeah? You're quiet. You see that? Okay. So, this is obviously true because we have 1 and 5, 1 and 5, and then we have something more. So if 2 and 4 are 0, like the do not exist, then it will have an equality. But if there are tables in 2 and 4, it will always be bigger. So it's obvious. There's nothing which is not obvious about 3 properties of an object. And all of them, doesn't matter which one you choose, will have this inequality. And now, of course, if we divide both sides of this inequality in the number of tables in the world, what we get is a different one. It says the probability. Now we have 10 tables in this set, and we divide by 100 tables. So it means 10% of the tables are in this set. 10 out of 100. So if we divide by n, we get the same inequality, but with probabilities. The probability of being a red table, but not square, plus the probability of being a table and not with 3 legs will be bigger than the probability of being, this was B, and A and not C. That's Bell inequality. And it's obvious, I can't see how anyone can argue against this. Venn diagrams are the most simple, basic logic of our world. Set theory is at the basis of all mathematics. You can't argue against that.
You do assume some kind of uniform sampling.
Yeah. I assume that all of these, we'll see that in a minute. Now the point, says Bell, if we now create these 3 spins that we want to measure, and there will not be x, y, and z. There will be A will be the spin on z direction is up. B will be the spin on 45-degree spin on the same plane. Is, I call it up, but it means it's like this 45 and not this 45. And C will be the spin on x direction is up or right, as you want, right and not left. 3 properties of the electron. If the electron has a real spin in 3-dimensional space, we can do the projection to each of these directions and we will know the answer. And we can count the number of electrons out of the million that we use in the experiment, like in the Venn diagram. The amount of the electron that has a spin z and a not spinning up 45, which means down 45. And therefore, we can calculate this into an experiment and see if they have a real property, like Einstein said. They must obey the electrons that we measure again and again and again. They must obey this inequality. Soon, we want to do it now, we'll do it now. Soon we will use quantum mechanics and say what's the probability of measuring spin z and spin this. We have all the predictions. And we'll see that quantum mechanics says that there is a situation where this is smaller than that one. Strangely enough, but that's the mathematics. So after we'll do that, that's a really ugly calculation, but we'll do it. It will mean that the spin is not a property. Because if it was a property, it had to really fulfill this inequality. We will show that we put the numbers and do the calculation, and we don't get that. And therefore, Einstein was wrong. There's no property. But if Einstein was wrong and there's no property, Einstein was right to say that there is a spooky action at a distance. Because if there's no property and this is the real property, it means that when Alice is measuring, this is really collapsing. Immediately. Something that she had done, if she wouldn't have done that, this will still keep going in this state. It's changing its state. The physical state of the system is really changing when Alice is measuring, and therefore something spooky is happening. Does that mean that we can communicate and tell you things in Mars in 2 seconds? we'll see that the answer in this experiment is no. But, and this is again something most physicists miss, and this is what often called non-locality. Something that happens here can influence the real system, not our knowledge of the system. The real system in 0 time. Okay? Again, let's think about, for 1 second said my socks are different, and that's like something that Bell wrote in one of his articles. But he had done a picture. If you take this book, let's say you stand outside, and I tell you that I woke up today with different socks. One is red and one is green. And he sees only that leg, and he sees green. He immediately knows that this is red, right? And this is not surprising. It's like that's like you'll see this picture in this book. But it's exactly the same as the 2 coins. You have 5 shekels and 1 shekel, and you do that, and you separate them to the end of the galaxy. It's immediately true that if I find out that this is 5, I immediately know that this is 1. But there's no spooky equation at the distance at all, because this was all along 1. I just didn't know it. So this is not surprising to Einstein. It's not surprising to anyone. You always have correlations. If you mix 5 and 1, and you're a complete realist, right? There is 5 and there is 1. You just don't know which one. And you open, you measure 1, you know it's 5, you immediately know this is 1. It's no surprise because you have a realistic picture. It was always, as I mixed them and went away, this was all along 1, no one knew it in the universe. And this was all along 5, no one knew it in the universe. When Alice measures 5, she immediately gains knowledge about what happens there, but she didn't influence the coin. It was not in a superposition, it was 1. So you can gain knowledge about things that happen far away, and that's not contradicting anything about reality. But if you insist that there is no property, so there's really superposition, and then you have a superposition in 5 and 1, and then Alice opens up and finds 5, it means that the superposition there, at this very moment, changed into 1. So something really happened there. Not just gaining knowledge about what was already there, but you're gaining knowledge which actually changed the state of the system.
So how do you settle it?
It's a good question. So this gang of people in the 60s, that's why they were hippies, as they read, by the way, Bell article also did not gain a lot of interest from physicists, but they were interested in parapsychology, in telepathy, in Uri Geller, and in communication faster than light. So they studied Bell really, really closely, Clauser amongst them, and Clauser said, okay, I want to do the experiment and see who's right. And both Clauser and Bell thought that they would prove that Einstein was right, so they will get this is bigger than that, unlike what quantum mechanics is saying. So now it's not a philosophical question of whether the situation when we don't look at it is superposition or real, but we always, when we look at it, now it's a question of an inequality. Like if you have 6 and 4, it's a real property. If you have 3 and 5, it's not a property. So now if it's 3 and 5, Einstein is wrong. Okay, end of story. It's an experiment saying Einstein is surely wrong. It doesn't matter if you're a Buddhist, if you like yin and yang, if you like all kind of strange things in reality. If there's a property, this should be bigger than that. Quantum mechanics says this is smaller than that. So either quantum mechanics is wrong, or quantum mechanics is right and this is not a property. If this is not a property, then there's a spooky action at a distance, then to them, relativity is wrong. So this is like a crucial experiment that decides whether quantum mechanics is wrong, relativity, the best 2 theories that we have, they cannot both be right.
So how come it's that the other physicists didn't know that it's very expensive, very valuable
I'll tell you in a
experiment?
moment, I'll tell you in a moment.
It's
For a
actually
while,
answering the question who is
For a
right.
while, Nick Herbert and others, they created experiments, real experiments, that they thought could signal faster than light. We can speak. It's not that difficult. Like, you do something here that it has a different effect here if it's superposition or not, and then you can see 0 or 1. Like, he can know whether she measured or not. In principle, it looked possible. Nick Herbert and other published papers about how to do that. They got they wanted to get grants from DARPA and others because it's the Cold War, you can signal to your submarines in 0 time, like, and it was very difficult to analyze why they're wrong. So initially they thought this Spooky action at a distance must allow us to communicate faster than light and see these things that creates really mess because of causality and everything. And then some people worked really hard to disprove them, to say this is not really happening for very difficult reasons, like in the physics of it. For example, Feynman read one of these articles and he didn't manage to say what's wrong, but others did. And one of the things that were wrong is no cloning theorem. So Zurek came up with the non-cloning theorem, which is at the heart of quantum computers, not to build a computer, but to prove that there is no communication faster than light. Okay. So all of quantum computing, and when they managed to understand that it seems to be impossible to communicate, they found out the encryption protocol that is called BB84, and therefore they asked for grants for encryption from the defense ministry and not for other things, and therefore quantum computing started, or quantum technologies. Yeah. And to do these experiments, one had to, the main barrier was to be able to create single photons in a superposition or entangled state, which they didn't know in the 1960s. So both Clauser and Aspe, all they've done was to create an entangled pair. And this technology that they developed to see whether Einstein or Bohr are right, and whether the entangled state, this is at the heart of all of the systems we use today for computing.
אני מצטערת על העברית, אבל הוצאתי כאילו שקל וחמש. א', זה לא אותו גודל, וגם לא אותו זה, ושבכלל הצורה של החמש היא נראית כמו עיגול, אבל
סתם היה דוגמה.
אבל דקה, כאילו אם אני מרחיקה אותה, סביר להניח שגם הצורה, גם העובי וגם הגודל יהיה שונה, וגם הקשר ביניהם יהיה שונה.
No, it doesn't matter. Take two balls, one is blue and one is red.
גם סביר להניח, צבע גם משפיע.
No, it doesn't. If you close it and you don't see it, it doesn't.
אבל בתוך החומר...
Red and blue doesn't attract each other differently from red and red. It doesn't matter to anything physical. It matters for the photons that come, but if you close it in a black box,
גם הצורה וגם העובי, זה לא שטח
take
קטנים.
two identical balls, one is blue and one is red, and you get the same argument. Doesn't matter. It will not help you. Put them in a black box, and no one can know what's the color, and then you have the same argument. Let's just have an example. Take two 1 shekels and put an X on one of them. Okay? Take them apart. Which one is with the X and which one is without? Doesn't matter. Okay. Usually when I start doing the calculation itself, I tell people you can close your eyes and go to sleep if you're of the kind of people that don't need to see the real proof, because it's really long algebra. So you can just go to sleep and wake up and believe me that this was 0.5, this will be 0.5, it's like 2 square root of 2. This is what was on the picture behind John Bell that they showed you, and this is something else, and you get this is smaller than that. No? If you believe me and you're the kind of people that don't need that to be convinced, you can go to sleep or go to eat. Now I don't know if I let everybody go and eat for an hour, and the people who want the ugly thing will get half an hour, or I'll punish all of you tomorrow. Because at 1:30 we meet Ben Kishi.
Can't you just share the proof on WhatsApp?
Well, it's kind of long, but I like to do it. It's kind of, I don't like not seeing it once. I cannot repeat it in my notebook, but to see it once in my life, it's kind of amazing, huh? To see that you know the mathematics and it really brings a smaller number on the left-hand side and a bigger number on the right-hand side. It's crazy, no?
That's the reason
You have all the tools to see.
That's
Now
the
you go
reason we
to
have all
sleep.
the tools, just to see.
There's nothing, almost nothing more amazing than that you can see in physics.
So let's go do it.
Tomorrow morning when you're fresh.
What's
Okay.
going to
And also Amit is coming at 1:30, so we want to start on time. So yeah. But that's the better inequality, and it's being broken by quantum mechanics, and therefore there is a spooky action at a distance. And many physicists will tell you, oh, yeah, there is spooky action, but we cannot communicate with it, so it doesn't matter. But
There is a spooky.
it does matter. So it's kind of suppressing and putting it under the carpet so we can go on and build computers. And it's a very interesting question because all of this book is about how technology influences physics. Like when you had the Cold War and you had to build radars on the no one had time and appetite to do philosophy. And then they started, apart from being hippies, at the late 1970s, Reagan administration at 82, and they cut the budgets of the physicists because they understood there's enough bombs. And then they didn't have positions and grants to do nuclear physics, and therefore they had more time to do this crazy stuff. And I think it's a real question now that you get billions. Like really, when I've done my master degree in 1990, and I was interested in entanglement because of this thing. In 1990, you already knew that it's happening, and there was one person aspect who knew how to do the experiment, and he showed that the experiment follows quantum mechanics and not. They told me, like many others, like go and do philosophy. It's not interesting. It's not practical in any way. And 30 years later, this is like people are raising hundreds of millions of dollars to build entangled pairs and to do computing with them. And it's a valid question now that the money is coming back, whether some of the money will go to people who will try to think again about spooky action at a distance, or the opposite, all the money will tell them, no, you need to build now 20 qubits and now 100 qubits and now fix the error and now do this and do that. I think if you look at the Israeli community, and I think also the Israeli community, like 99% of the people who knows this physics are doing computers and not what Akira Aronov and Avshalom Elitzur are thinking about. It's an interesting question to play with Amit, who has a PhD, worked in Rafael for many years and now building a computer and CTO, to ask him about spooky action at a distance between the ions that they have. I never asked him about that theorem, so I don't know what he knows and what he doesn't know and what he cares about. But it's a valid question for the future. Okay. Eating 1:30, we start with the meeting.